Now, now it's recorded, and now please start your talk. Thanks.
Okay, good. So a lot of the things that I'll be talking about, some of you maybe have seen, but if not, please feel free to interrupt me, ask questions at any time. So I'll proceed slowly and in a way that's hopefully pedagogical. I take it's about 1 hour, right? So if I go beyond 1 hour, please let me know to like either speed up or cut off or whatnot. All right, so hydrodynamics clearly has a lot of practical applications. And as a theoretical physicist, you can ask, why would you care about hydrodynamics? Hasn't the theory been established a long time ago? And for me, personally, I have two answers to that. One is that I care about the applications. And two, you want to understand hydrodynamics at a deeper level. And this, this is holotube. So I take it lots of people are interested in holography. This talk will not be about holography. However, I believe that there is still for holography to add insight into hydrodynamics in spite of a lot of work that has been done already over the years. Most applications of fluid dynamics are based on this paradigm. The paradigm goes like this. Hydrodynamics is a collection of partial differential equations. And indeed, in the first part of the talk, I will focus on that particular paradigm and then move away from that later. So within that paradigm, you work like this. So step one, you identify the physical system. Step two, you solve the hydrodynamic equations. And step three, you extract the interest in physics. So what is step one? What is the physical system that you are interested in? Well, it sort of depends. It's up to you. So I personally am interested in extreme matter, matter at high temperature, high density. So matter made out of quarks, gluons, so both relativistic and quantum. And the poster child of that extreme matter is the quark-gluon plasma. This is something that I imagine many people have seen many times already over the years. And, there are many statements that have been made about the quark-gluon plasma. It is like the hottest liquid, the most vertical, has highest magnetic field. But this statement that is perhaps most widely used, or at least has been used very widely in the past, is that, so as this quote says from this article in Scientific American, it's probably the most perfect liquid ever observed. Perfect liquid meaning small viscosity. So our poster child is characterized by two, very distinctive things. It is a relativistic fluid, and it has very small viscosity. Okay, so now let's look a little bit deeper. Let's open some closets. So what lurks in the closet? So it depends who you ask. If you ask experimentalists, they will tell you about their own characters that live in this closet. And if you ask people who work on phenomenology of extreme matter, they will tell you about their own favorite characters that live in this closet. However, even if you sort of self-identify as a formal, quote-unquote, theoretical physicist, there are still some characters that you can find in there, and I will talk about two of my favorite characters. One pertaining to relativistic fluid, and the other pertaining to small viscosity. So, okay, so relativistic fluid. So what is it? So let's say you're a student in subatomic physics or astrophysics. You want to learn about relativistic Navier-Stokes equations, and as a student, maybe you are tempted to learn from textbooks. Well, when I was a student, there were still textbooks at the time. So you open Fluid Mechanics by Landau-Lifshitz, and you see some equations. And then, you may have other books. I also had the Gravitation and Cosmology by Weinberg. And also, you see some equations in that book. Then you decide to compare the two, and you realize these equations look very different. So as a student, it's natural at that stage to be confused, but also as a student, you are taught to shut up and calculate. So let us shut up and calculate, and let's work out a very, very simple example, namely linearized infinitesimal perturbation of the thermal global equilibrium state. And this is an exercise that you can do quite easily. And when you do this exercise, you realize that both Landau, Lifshitz, and Eckart's equations, they predict two things. Number one, they predict that thermal equilibrium does not exist. And number two, they predict that things propagate faster than light, which is not good in a relativistic system. So what exactly is the problem? So one way to see the problem is when you look at small perturbations, you think about plane waves, exponential minus I omega t plus ikx. And when you solve those hydrodynamic equations, you find the dispersion relations, omega as a function of k. And when you look at this omega as a function of k, there are two kinds of modes. So one kind of modes is so-called gapless modes. This is when the frequency goes to zero as the wavelengths becomes larger and larger. So these gapless modes exist because of conserved charges, and they correspond to normal hydrodynamics, such as sound waves, etc. But the equations also predict gapped modes. This is such that when the wavelengths becomes larger and larger, the frequency stays finite. And moreover, there will be gapped modes in those hydrodynamic theories with positive imaginary part of the frequency. So these are unphysical modes. These modes, you can call them fake modes. They are outside of the validity regime of the low energy hydrodynamic approximation. These are UV modes. So if you are an effective theorist, you say, I should not trust those modes. And that's right, you should not trust those modes. In the extreme low energy regime, you're not supposed to believe any UV physics. But if you actually want to solve the equations in practice, these unphysical modes ruin predictability for you. And so what this means is that you cannot just throw away those modes out of the equations. The equations are there, you have to solve them as a whole. And because these modes exist, you end up not being able to solve them. And so from an effective field theory point of view, you can say that this is a situation where cutoff scale physics messes up the infrared behavior. So you can ask this question, does relativistic hydrodynamics even exist? So what does this mean? Of course, if you talk to practitioners who solve the hydrodynamic equations, then very soon you realize that the classic textbook hydrodynamics is not what you solve in practice if you want to, say, study the quark gluon plasma. So you do not solve what you find in the textbook. So most popular fix to those problems is not the normal hydrodynamics, is the so-called Israel-Stewart theory. And so the way it works is that you take your hydrodynamic equations and you couple them to extra UV degrees of freedom. And this extra UV degrees of freedom, they conspire in such a way that they kill the unphysical UV modes. So this is sort of very reminiscent of what you do in quantum field theory, when if you want to regulate your theory in the UV, you add heavy particles and engineer them such that the UV is well behaved. So this extra degrees of freedom in the case of hydrodynamics, they of Israel-Stewart hydrodynamics, they are the dynamical stresses, heat fluxes, in addition to what you're normally used to, such as, you know, density, temperature, velocity, and whatnot. So this extra degrees of freedom, they play the role of a UV regulator in the Israel-Stewart theory. And this is something new that you don't see in normal non-relativistic Navier-Stokes. In normal non-relativistic Navier-Stokes, you don't need these UV regulators. But as a student, you still have this nagging question, okay? Even after you realize that you don't solve the textbook equation, so why does the theory of Landau-Lifshitz differ from the theory of Eckart? And so to understand why, let's talk first about physics. Okay, so the easiest thing to understand is temperature. So let's look at this cartoon for a minute. Okay, so what this sort of tells you is that how you measure temperature is important. So measurement is important. And so if you think about how you measure temperature in practice, you think about it that temperature is something that is only unambiguously defined in equilibrium. Okay, so this is what we teach our students. Temperature is by definition the quantity that is measured by thermometer. So what is a thermometer? Well, a thermometer is a little heat reservoir that you bring in heat contact with your system. So here I have a cartoon of two boxes, and the orange stuff inside the box is my system, and the little blobs are two different thermometers. So I have a red thermometer and I have a blue thermometer. And the thermometers are coupled to gauges. Here, this white gauge, this is something that measures temperature. And in identical equilibrium states, these two different but properly calibrated thermometers will show exactly the same temperature. That is to say, it doesn't matter what the thermometer is, the temperature will be the same. If you calibrate them, you are in equilibrium. Well, now let's say you are out of equilibrium. And now let's say you have two identical out of equilibrium states that again showed by these two boxes, and you have the same non-equilibrium matter in the same non-equilibrium state. And you place the same two thermometers in your boxes, and now the thermometers will show different temperatures. Now, why is that? Well, you know this very well if you have two different thermometers outside your window. For example, if the temperature, drops very quickly or rises very quickly, then one of these thermometers maybe takes longer time to respond to temperature changes. Also, if there is wind blowing and maybe one thermometer is, very large, and the other is very small. So because of small gradients in temperature that exist because of the wind, they will measure slightly different temperatures. So this is sort of physically understandable. However, there exist ambiguities even in equilibrium. So even in equilibrium, there is not a unique definition of temperature. And perhaps the easiest way to understand this in a relativistic system is to imagine that you have some object that is massive, that produces a spherically symmetric gravitational field, like I have here in the picture on the right, a star or a planet. And I have my stuff, which is indicated by a grayish halo here. So this is my matter subject to that external spherically symmetric gravitational field. So in this case, this will be the Schwarzschild metric outside my planet. And let's say it's some relativistic matter. So let's say it's radiation with the equation of state when energy density is 3 times pressure. So what is the equilibrium temperature of my matter? So one sort of conventional way to define temperature is to say, well, okay, so everything is in static equilibrium. So there exists a Killing vector that tells you about the direction of time, Killing vector v. The fluid velocity is the norm of, it's a unit vector, so it has to be the normalized Killing vector. Just tells you it's the rest frame of the fluid. If nothing, it moves. Your rest frame points in the direction of time. And then the fluid temperature is basically 1 over the square root of minus v squared, so that you match the normal canonical ensemble, exponential minus beta h, where beta is the inverse temperature. And this gives the so-called Tolman's law of temperature, spatially dependent temperature in external gravitational field. So this is the definition of temperature that is advocated, for example, in Landau-Lifshitz volume 5, statistical physics. This definition of temperature can be explored at length if you go beyond, zeroth order hydrodynamics, you can go to second order hydrodynamics, figure out different relationships between susceptibilities. So this has been discussed in great lengths in these two papers. Some of the authors may be in the audience. So this is one way to think about temperature in equilibrium. However, if you open the textbook of Landau-Lifshitz, volume 6, not volume 5, but volume 6, fluid mechanics, they do slightly differently. They do something slightly different in fluid mechanics. So in fluid mechanics, they have their own definition of the fluid's temperature and fluid's velocity. There is a certain convention that is called the Landau-Lifshitz convention or Landau-Lifshitz frame. And what you can do, you can work out what the energy momentum tensor is in static equilibrium in the Landau-Lifshitz convention when the matter is subject to external gravitational field. So here P is pressure as a function of temperature, L stands for Landau. So 4P is here because of the matter is conformal, because of the equation of state. U is the fluid velocity. And here you have the gravitational invariance, so Riemann tensor and whatnot. So there is an extra coefficient here, which was, I think, first discussed in this paper, BRSSS, and also in the corresponding fluid gravity paper. So BRSSS, I guess, again, some authors may be in the audience, call this kappa, the gravitational susceptibility. That's one of the quote-unquote second-order transport coefficients. And so you can ask, given this energy momentum tensor of a fluid that is subject to a spherically symmetric gravitational field, what is temperature? Well, you're supposed to figure out what temperature is by solving the conservation for the energy momentum tensor. And if you parameterize your temperature, TL, Landau's temperature, as a function of R, in this way, so you stick in minus G naught naught in the denominator, as you would normally do, and then you have some function, h of R. So if this h of R is equal to 1, you have the normal Tolman's law that is advocated in Landau-Lifshitz volume 5. So here, you just take this temperature, stick it in the energy momentum tensor, solve for the conservation of T mu, and you find this little h. And what you find is that this h is not 1. There is a simple differential equation for h that you can derive. You solve it, and here is the answer. So this plot here shows this little h as a function of R, measured in units of the Schwarzschild radius. So Ls is the Schwarzschild radius. The equation of state is pressure proportional to temperature to the force. By conformal invariance, this little kappa, this susceptibility that sits in front of the gravitational quantities, is proportional to T squared. By conformal invariance, there is some dimensionless coefficient kappa naught. And you can form this dimensionless quantity made out of the gravitational susceptibility and the pressure. This is going to be some dimensionless number, like there's some answer for it is in the actual black body radiation. It has been computed in a gas of photons, some dimensionless number. And then depending on what this epsilon is, you plot h as a function of R. It goes to 1 at infinity, away from the planet as it should be. And so the way you look at this is that when this little h is not equal to 1, it parameterizes the difference between the definition of temperature used in Landau-Lifshitz volume 5 and in Landau-Lifshitz volume 6. Of course, they don't tell you that they use different definitions of temperature, so unsuspecting students, beware, this temperature is slightly different. I think it's hopefully clear that there is a certain arbitrariness in what you mean by fluid temperature, and that is because your choice of a thermometer is a convention. There is also the same arbitrariness in what you mean by fluid velocity. Also, your choice of a velocimeter is a convention. And what happens is Landau-Lifshitz version of Navier-Stokes use one convention, Eckart's version uses another. And there is no such thing as quote-unquote the Navier-Stokes equations until you specify your arbitrarily chosen convention. So what is important is that these different conventions, they give rise to different mathematically inequivalent Navier-Stokes equations. So the conventions have real consequences. And this is, of course, because the Navier-Stokes equations only give you a crude approximation of a real fluid, and the difference between the conventions is hidden in the crudeness of this approximation. So both Landau, Lifshitz, and Eckert, they adopt different conventions for relativistic Navier-Stokes, but both of these conventions are bad, and both lead to nonsensical predictions. So what exactly is wrong with the classics? So one way to understand this in sort of cartoonish terms is that both Landau, Lifshitz, and Eckert, they define temperature by the following equation. They say that the exact non-equilibrium energy density is equal to E of t, where this function is given by the equation of state. And what this means that as the local density of energy changes, the thermometer adjusts its temperature instantaneously. Okay, there is no delay at all. So because the exact non-equilibrium energy density, say if you wish, the 0,0 component of the stress energy tensor in the appropriate coordinates is given by this E of t, just some algebraic function. And if you work out the details, it so happens that such thermometers that react instantaneously, that they violate relativity and lead to superluminal propagation in relativistic fluid dynamics. So what do you do with this in practice? So let's remember what we do in field theory. So what we do in field theory, we follow the 4 steps in effective field theory. You identify the low energy variables. You write down all the terms that are allowed by the symmetry. You do this up to a given dimension. So here is the normal phi to the 4th theory in 4 dimensions. And then you look at the coefficients in your action and you constrain this coefficient so that the physics is sensible. For example, this C less than 0 is what you need in order for the vacuum to be stable. So let's do the same in hydrodynamics. So you identify the low energy variables and the conventional variables. I mean, they don't have to be these particular variables, but let's stick with the conventional choice, which is temperature, fluid velocity, and the chemical potential. Then you write down all possible terms in the constitutive relations that are consistent with the symmetry. So you do this up to a given order, say first order in the derivative expansion. And then you constrain the coefficients of what you have in the constitutive relations so that the physics is sensible. So for example, you demand that the equilibrium state is stable, just like in normal effective field theory, you demand that the vacuum state is stable. So let's look at a very, very elementary example of diffusion. So diffusion is something what happens when you have a conserved current, say U1 particle number current. So time derivative of charge density plus the divergence of the flux is equal to 0. And so let's say we work with some auxiliary quantity, chemical potential, when you express both the density and the flux as functions of this chemical potential. Okay, so the flux is a vector, so you write it with a gradient of mu to make a vector out of a scalar mu. So you stick in some coefficient out in front, which is the conductivity. And then the charge density, when expanded about the equilibrium, will have a small fluctuation delta mu in here with some coefficient, which is susceptibility. And then also by rotation invariance, you can add a term that has a time derivative of the chemical potential. So normally this term, you don't take it into account, you just neglect this. And if you ignore this term with the time derivative of the chemical potential, you get the normal diffusion equation. So this is the standard physics of diffusion that you get with this gradient of the chemical potential in the flux. Diffusion constant is proportional to the conductivity sigma. However, if you choose to keep this term, and no, this is also technically a one derivative term, depending on how you count, but if you count one derivative, time and space on the same footing, then this is a one derivative term. You stick it into your conservation law, and then you have, in your equation, you have both the second time derivative and the second space derivative, so your equation is hyperbolic. And what this tells you is that, okay, so you add this one derivative term and it changes your equation from being parabolic to being hyperbolic. Now, why don't you normally care about this term? And normally you don't care about this term because this term with the time derivative can be eliminated by field redefinition, where you redefine mu by derivative correction and truncate the derivative expansion. So this term with time derivative of mu is not a physical term for the purposes of computing correlation functions in the low energy physics. But it does change the structure of your PDE. And if the question that you're interested in is the question of solving PDEs rather than evaluating correlation functions, then this term with a mu dot, it does make a difference. And because this term can be eliminated by field redefinition, so one way to think about this term is that this coefficient can be interpreted as specifying your quote-unquote mu meter, just like similar terms that come with temperature will tell you about the specification of your thermometer. All right. So you can say, what about kinetic theory? Isn't hydrodynamics derivable from kinetic theory? Isn't this, you just take Boltzmann equation and you get the Navier-Stokes out of this? So how does this work? And indeed, you just take the Boltzmann equation, which is this. So F is the one particle distribution function, P is the particle's momentum. The Boltzmann equation says this derivative is equal to some collision term that is usually some integral of the products of this distribution function. The energy momentum tensor is made out of the one particle distribution function like this. And the important thing is that the C, the collision term that sits in the right-hand side of the Boltzmann equation, is not arbitrary. It must be such that it respects the microscopic conservation laws of energy momentum and particle number. So when you have collisions that are described by this collision term, these collisions are such that they respect conservation of energy, momentum, and particle number. And if these properties hold, then this collision operator must have this property. So you integrate it with P, and A and B are arbitrary functions of X, and the conservation of energy, momentum, and particle number tell you that this is going to be true. And this is what is needed to argue that the energy momentum tensor is conserved and the particle number current is conserved with any distribution function. But what this will tell you, what this property will tell you when you solve the Boltzmann equation, it will tell you that the solution, the distribution function, the solution will contain arbitrary functions of X. One way to think about them is this arbitrary functions of X are integration constants in P. So really what you're solving for, the real difficulty is to figure out the P dependence. And when you integrate in P, you will find some integration constants, which are not constants, but are functions of X. And these arbitrary functions of X are precisely the field redefinitions of the hydrodynamic variables that, as I kind of advocated, it's not unreasonable to interpret them as specifying your thermometer, velocimeter, and whatnot. You can also say, what about fluid gravity? Can you derive, Navier-Stokes from fluid gravity? And indeed you can. What you do is you solve Einstein's equations in the bulk, order by order in the derivative expansion. And there is going to be a certain, differential equation that is needed to solve, each of those corrections. And there is going to be some differential operator that acts, on this correction, gives you some source on the right-hand side, and that differential operator, will have zero modes, just like the collision operator for the Boltzmann equation will have zero modes. And because of the zero modes, the solutions for the metric will contain arbitrary functions of X. And this has been emphasized even in the very first paper on fluid gravity in 2007. And so these arbitrary functions of X that appear in the solution of your metric, they will be again exactly the field redefinitions of the hydrodynamic variables. So the claim is that the simple example of diffusion that I mentioned, it can be generalized to the full nonlinear relativistic hydrodynamics. It actually works. You can make these field redefinitions so that there is no need to introduce any extra degrees of freedom like you do in the Israel-Stewart theory. So you simply have normal relativistic Navier-Stokes with the cleverly chosen, thermometer velocimeter. And if you want to, if you want more details, you can look in these papers. So you basically get relativistic Navier-Stokes equations, which are not Israel-Stewart. You can actually solve them numerically. Earlier this year, Franz Pretorius and his students, so they had a paper exploring this set of equations in this with cleverly chosen field redefinitions and comparing them with Israel-Stewart, and the structure of the equations is different, but they're amenable to numerical simulation. And you find what you expect to find is that in the low energy regime, both this Navier-Stokes and Israel-Stewart, they agree. There are sort of disagreements when you look at higher gradients, but the equations do what they're supposed to do. Another picture that I like to show is that, so this is a picture from, again, earlier this year in the spring, is that if you look at the state-of-the-art simulations of the quark-gluon plasma done with the Israel-Stewart theory, they're also not that, immediately clean because they violate causality. So what you're looking at here is you're looking at kind of the collision of two nuclei in the plane that is transverse to the nuclear. So the nuclei collide like this, and you look at them, from the axis of the collision. These simulations are done using different hydrodynamic codes for heavy ion collisions with different initial conditions. And they're done using the Israel-Stewart theory. Of course, the Israel-Stewart theory, like all hydrodynamic theories, it's not like it's good or bad. It comes with its own parameters, and these parameters must satisfy, certain inequalities in order for the partial differential equations to be hyperbolic, in order for the system to be causal. And what you're looking at here, you're looking at regions in real physical space. So this is X in real physical space that are colored depending on whether the parameters in the Israel-Stewart equations respect causality or violate causality. So the red regions here are the regions where causality is violated. In other words, the parameters that sit in your equations, they fall outside of the necessary conditions that you must have in order for your equations to be hyperbolic. The blue regions are the regions where causality is preserved, and the purple regions are the regions where they cannot tell. Okay, so the only reason I'm showing you this slide is to emphasize that the whole question of whether your equations are causal, whether the actual simulations are consistent with relativity, it's more subtle than what you might naively expect. So you need to choose certain set of parameters for Israel-Stewart. You also need to choose certain sets of parameters in the Navier-Stokes. All right, so the question, yep.
So in these pictures that you showed,
yep.
So is this tau, I guess, is the time, right?
Yep.
So can I understand this as that hydrodynamics is more and more applicable as time passes? I mean, for early times, I don't expect hydrodynamics to be applicable, right?
So it depends on how you want to view this. So I would say that even if you don't necessarily, so first I would say the problem is not necessarily with early times, but with what you can see here is with the edges. So edges is where problems happen. But I would add that even though you don't necessarily expect hydrodynamics to be always applicable, the theory that you are using to study hydrodynamics at least must be consistent with relativity. So you must have a consistent relativistic theory, even though the theory, may not describe what you want, but at least you want to get the symmetries right. And the subtlety here is that even if you write down your equations, with all the indices, in proper places, and all your fields transforming in the right way, it is not the same as having relativistic causality, because it is one thing to have an equation that sort of looks right, and it's another thing to say that these equations admit a well-posed initial value problem, the notion of light cones, the notion of causality. So this is not one and the same thing, right? And so these pictures that pertain to the latter question.
Okay, and is there any intuition of why I recover somehow causality for late times?
Well, it's kind of things slow down, gradients smooth out. So this is the intuition. Okay. But the way I would interpret these pictures is not something that this red regions is not necessarily something that tells you about the breakdown of hydrodynamics. It is something that would tell you about that the theory needs to be fixed. So let's fix the theory first, so that it's always admits well-defined initial value problem. And then with that fixed theory, we can talk whether that theory describes the physics that we want to describe.
Okay, thank you.
So, what seems to happen with all these relativistic hydrodynamic theories is that relativistic hydrodynamics seems to require that the equations contain non-hydrodynamic parameters. So these non-hydrodynamic parameters are the parameters that specify your thermometer or your velocimeter. There are also these non-hydrodynamic parameters that sit in the Israel-Stewart theory, the relaxation times, that again have to obey certain inequalities. And somehow seems like you cannot get away from those non-hydrodynamic parameters. So if your equations have non-hydrodynamic parameters, then your solutions also depend on those non-hydrodynamic parameters. And then you can ask, does hydrodynamics actually have predictive power? Because you want to view it as a low energy theory, but the low energy theory somehow seems to contain this high energy physics. And so how do you get rid of the high energy physics by keeping the lower energy physics intact? And in quantum field theory, you do this with certain normalization groups that ensures that the low energy physics is independent of the UV regulator. And how to do this in general with these partial differential equations of relativistic fluid dynamics, I'm not sure. In simple examples, you can perhaps argue for the procedure, but in general, I don't know. So suppose you can make sense out of hydrodynamics, Israel-Stewart or Navier-Stokes or whatnot, and then the second item of our poster child, the quark-gluon plasma, is the viscosity. So you need to know what is the viscosity that you must plug into those equations. So is viscosity measurable? Is it computable? And viscosity is something that tells you about the transfer of momentum between different layers of fluid. And so what I have here on the left is a picture of fluid moving from right to left. So fluid moves fast on the bottom, moves slow on top. So the yellow arrows is the fluid, and the thin blue arrows are the particles that jump between different layers of the fluid and transfer momentum. So the mean distance that they travel is what people call the mean free path. And in a gas, the viscosity is proportional to the mean free path. And I'm sure that many people have seen this estimate that the viscosity over entropy density is roughly, must be bigger than h bar. Because of this mean free path here. And in holography, it's 1/4 pi, it's order h bar times, numerically small number. So this is kind of standard. What is sort of less standard is that is to realize that momentum can also be transferred by collective excitations. And what I have here is the same picture, except for particles have sound waves that travel back and forth. In a gas of sound waves, the mean free path, how far they travel, is now inversely proportional to the viscosity k squared, because that's what determines for you the dissipation of sound, viscosity times k squared. K is the wave vector. And if you want to look at the contribution of all those sound waves to viscosity, you sum over all possible wave vectors. So say in d space dimensions, you integrate over k. And then what you find is that, okay, so the integral is uv divergent in 3 space dimensions. And it's inversely proportional to viscosity. Okay, so this is already interesting, but what's more interesting is that in 2 space dimensions, this integral is actually divergent in the infrared. And infrared divergences are kind of more interesting than UV divergences, so they tell you there is some macroscopic physics that you don't necessarily understand. So what this is the physics of thermal fluctuations. This is something that you do not see if you merely view hydrodynamics as a collection of partial differential equations. And so what this tells you is that classical hydrodynamics beyond Navier-Stokes may be invalid in 3 space dimensions. So I'll comment about that later. The Navier-Stokes hydrodynamics may actually be invalid in 2 space dimensions because of that infrared divergence. Again, this is something that people have started to study in great detail even in the 1970s. And my last comment is that, remember our quark-gluon plasma was supposed to have very, very small viscosity. Now, if you look at, this formula here, so the smaller the viscosity is, the larger this fluctuation correction is. Okay, so if you want viscosity to be small, then your correction is going to be large. So if you think that viscosity can be arbitrarily small, then you have to think again. So alternatively, so you can ask this question. So it's sort of the same question, but asked from a different angle. So suppose you want to look at very simple solutions of classical hydrodynamics. So how near equilibrium physical system reacts to infinitesimal external sources. That's what you can do in ADS-CFT. That's what you can do in classical system. So when you look at how the system responds to external sources, you get the response functions. So this classical fluid dynamics gives you predictions for retarded functions of energy density, it has some diffusion singularity here, or retarded functions of stress, there's some pressure here. And these do not depend on which version of hydrodynamics you're using, Israel-Stewart, Navier-Stokes, whatever. So they're all going to be the same in the low energy regime. And so these are universal predictions of just normal conventional textbook hydrodynamics. So you can ask, are these predictions actually correct? We are theorists and we like to play with toy models. And after all, classical hydrodynamics, meaning hydrodynamics as a collection of partial differential equations, is just a toy model of fluids, and nature may or may not care for our toy models. And in fact, what started this whole field in fluid dynamics are observations in molecular dynamics simulations that were done in the 1960s. So people really just took a bunch of billiard balls and say, if you look at correlations in those billiard balls, do these correlations agree with Navier-Stokes? And they do not. So even if you're interested in macroscopic long-time, long-distance response near static equilibrium, then the classical equations which ignore fluctuations can give you predictions which are qualitatively wrong, not quantitatively, but qualitatively wrong. So in other words, there is infrared physics, not UV, but infrared physics that is not captured by classical hydro at any order in the derivative expansion. And the rest of my talks will be comments on this claim. So the first thing that you will see when you start when you start studying these fluctuation effects is the so-called stochastic hydrodynamics. So what is it? It's basically you take your classical hydrodynamics, classical energy momentum tensor with, Navier-Stokes, whatnot, and you add to it some randomly fluctuating variables, some random stresses here or random currents. And these are random, meaning you need to take an ensemble average over realizations of those stresses and currents, and you average over those noises with some weight. So you do a path integral over those things. There's some action, some weight in the path integral. And this action, if you look at the lowest energy hydrodynamics, this noise action is Gaussian, meaning it is quadratic in its variables. And you can argue sort of hand-wavingly that it must be quadratic by the central limit theorem, because when you look at large volumes where your fluid flows long wavelengths, there's going to be a large number of correlation volumes that fits inside one wavelength. And so when you average these uncorrelated fluctuations, you're supposed to get something that's Gaussian. Now the width of this Gaussian is determined by demanding that the equilibrium 2-point function satisfy the fluctuation dissipation theorem, which is the relationship between the symmetrized function and the imaginary part of the retarded function. And when you look at the applications of these ideas of stochastic hydrodynamics, say to the computation of viscosity, then the way it works is that, okay, so your energy momentum tensor will have some, linear things that relate to sound waves, for example. It will have these random noises, but it will also have, the standard thing that is required by boost invariance, energy density plus pressure, Vi, Vj, like the normal equilibrium energy momentum tensor. And then once you realize that, these velocities fluctuate, you can take this stochastic theory and sort of rewrite this in the Feynman diagrammatic form, where the tree-level contribution is going to give you what you thought was your normal viscosity. And the one-loop contribution, where you have energy density plus pressure at the vertex here, from here you have two velocities coming out of the vertex here. So this will give you the one-loop diagram that gives you this this correction to viscosity. So once you evaluate that one-loop diagram, this will get you to the correlation of stress. So here's this correlation of stress in 3 space dimensions. So what is highlighted in red is whatever is coming from classical hydrodynamics, zeros, first order, second order, and what is highlighted in purple is whatever is coming from that one loop diagram. This is going to be a correction to pressure due to fluctuating sound waves. There is going to be correction to viscosity that is dependent on the UV cutoff, T, which is fine. It's an EFT, which is this is inversely proportional to the viscosity. Then in 3 space dimensions, there is going to be a fractional power of frequency. And this is a universal cutoff independent contribution with a well-defined coefficient made out of 2's and pi's that is actually more important than second order hydrodynamics. So this is one loop correction to this response function, and if the actual measurable viscosity, it will include all of these corrections. So what you measure is whatever sits here in this parenthesis, not just these things individually. And as expected, small eta over S implies large corrections to eta over S. So this tells you if you really want to think arbitrarily small viscosity, you cannot do away with classical fluid mechanics. Fluctuations are mandatory. Fluctuations are actually more important than second order hydro because of this omega to the power 3/2 is more important than omega squared. So in time, this fractional power gives you 1 over t to the power 3/2 decay of fluctuations. This is what people call long time tails. In 2 space dimensions, you will get a logarithmic divergence instead of omega to the 3/2. So this will tell you that the Kubo formula for viscosity does not exist. And in holography, you normally do not see these things because the large n limit does not commute with the hydrodynamic limit. And in classical holography, you take n to infinity first. and then you take the hydrodynamic limit. So these fluctuation effects, they tend to go away. So this is a neat analogy with quantum gravity, which I'll probably skip in view of time. Once you compute loops of gravitons rather than loops of sound waves, you morally speaking get the same physical effects. So the bottom line is that classical hydrodynamics, meaning hydrodynamics as partial differential equations, if you try to use it to evaluate the response to infinitesimal sources, it is not reliable to do so in the extreme low energy limit. And short time statistical fluctuations give rise to infrared late time correlations. So these deviations from classical hydro are more pronounced at small viscosity. And stochastic hydro will predict that these infrared correlations are universal. They're determined by thermodynamics and transport coefficients such as viscosity, conductivity, whatnot. So this is kind of more or less like oldish like stuff that is familiar to many people. But let's dig a little bit deeper. So what if you want to go beyond this naive picture? Now, this noise action is only Gaussian in the extreme long wavelengths limit, again, by the central limit theorem. Now, what if you want to go with the derivative expansion? So you go, Navier-Stokes, maybe go to derivative hydrodynamics, maybe beyond that. Then this means that, you're interested in shorter and shorter wavelengths. And what this means is that beyond this strict k goes to 0 limit, your noise actually may not be Gaussian. So you must take into account, or it's conceivable that you will have to take into account the non-Gaussianities of the noise. Now, the width of the Gaussian was fixed by the fluctuation dissipation theorem for 2-point functions, but these fluctuation dissipation theorems actually exist for all n-point functions, not just for 2-point functions. So what do you do with those n-point functions? How do you impose the fluctuation dissipation theorems? Classical hydrodynamics can only compute retarded functions. Non-retarded functions are not visible, simply not visible. I mean, you have to play with fluctuation dissipation theorem to extract things such as, the symmetrized function. However, if you look at, 4-point functions, for example, then 4-point functions, non-retarded functions, they're not related to the retarded functions by the fluctuation dissipation theorem. So you have these non-retarded functions that you can evaluate in the lower energy limit. So they contain low energy information, like arbitrarily infrared information. But classical hydrodynamics is completely blind to that. So how do you access that information that is invisible to your classical description? And what you will do is, or what you want to do rather, is you want to do some sort of effective field theory. So effective field theory is what we normally do if we want to compute, response functions or correlations. So you identify the low energy degrees of freedom, you identify the symmetries, you write down a local action invariant under those symmetries, and you get correlation functions by taking the variation of the generating functional with respect to the sources. Okay, so psi is the degrees of freedom that you're fluctuating over. So can you do the same for near equilibrium states? Okay, so in this effective description, the classical hydrodynamics will be the Euler-Lagrange equations of motion. So that stochastic hydrodynamics emerges as a leading truncation. And I think there have been, 1 or 2 talks about this effective field theory of hydrodynamics on holotube, but not perhaps so much about applications of that formal theory. So what do you do with this? So how do you build this theory? So okay, so you want normal symmetry, locality, gauge diffeomorphism, invariance. You want the Euler-Lagrange equations of motion to be the conservation laws, conservation of energy momentum tensor, conservation of the current. This is different from how we normally teach classical mechanics. So when we teach classical mechanics to our students, we say, okay, so we have the equations of motion, the Euler-Lagrange equations, and then they imply the conservation laws. But here we want to be more clever. We want the conservation laws to be the equations of motion. You want to access real-time correlation functions, including the non-retarded functions. So hence, what you will do, you will formulate your effective field theory on the Schwinger-Keldysh contour with two sets of fields. And if you are in equilibrium, which again is the simplest possible situation you can think about, then you want to impose Kubo-Martin-Schwinger conditions as a symmetry of your action. Martin, how much time do I have?
Yeah, you have still 5 more minutes, but you can also go a little bit longer.
Thank you. All right, so I'll very quickly go through the construction of this EFT. So this is perhaps the most important brown or gray box that sits here. So you want you want an action that is gauge invariant. And the way this EFT works is that if you look at your external gauge field, you introduce a dynamical field, which is a scalar, and you form this kind of B, which is A plus D phi. And you write your effective action in terms of B rather than in terms of A. Okay, so then this action will be gauge invariant, and the equations of motion will be the conservation of the current. So this is the most important thing of how these actions are built. You can generalize this to diffeomorphism with the metric and other variables, but this is sort of the most important step. Then the other steps is that you need two sets of those fields. Schwinger-Keldysh, you label them 1 and 2. Or you can look at the sum and the difference, which is R is the sum and A is the difference. And then the last ingredient is what people call the KMS symmetry, is the certain symmetry that is needed to ensure that the fluctuation dissipation theorem holds. So think about the symmetry of the action as something that ensures for you the fluctuation dissipation theorem for all endpoint functions. So R is, remember, is the sum of the two fields that transforms into R, and A transforms into A plus time derivative of R. And I'm taking this formulation of effective field theory from a series of papers of Honglu, Glorioso, and Crossley. So I will skip the discussion of diffusion in stochastic hydrodynamics. I'll jump to the discussion of diffusion in effective field theory. So what you're looking at on this slide is you're looking at the effective Schwinger-Keldysh action for simple diffusion, like the same diffusion that you have learned, everybody has learned as undergraduate. So this is that normal diffusion. So this is the effective action. So remember, B is this combination. If there is an A, this means there is an A-type gauge field for the difference. If there is an R, this means there is an R-type gauge field for the sum. And if you think about this a little bit, this mu is the chemical potential, n is the particle number density, sigma is the conductivity as a function of the chemical potential, T is the temperature. The equation of motion that comes from this action will be the diffusion equation, and more importantly, all the correlation functions will be the correlation functions of diffusion, and it will match the stochastic hydrodynamics, like in the spirit of Landau-Lifshitz and others. Then what I have here is I have correction to diffusion. And so this correction to diffusion is made out of this A-type fields and R-type fields. Now, the reason I'm writing down these terms the way I do is not because I'm just writing down terms with like arbitrary coefficients. I'm writing down terms that are consistent with the symmetry that I impose, which is the KMS symmetry. And so the way to see that in this action, these two terms are KMS invariant is that the first transforms into a total derivative, and the second two terms, this BA and this parenthesis, they transform into each other. And in the second action, in the first line, this first box under KMS, it changes into stuff that is orthogonal to the second box. And here in the second line, these two boxes transform into each other. Now, why am I writing down these two terms? So what is the physical significance of those terms? So the physical significance is that these terms have more A fields than this one. And because they have more A fields, if you work out the equations of classical hydrodynamics, they will not contribute to equations of classical hydrodynamics. They, moreover, the second line will contribute to the non-Gaussian noise. The first one, the noise is Gaussian, but it is something that is not visible to the classical diffusion equation, because the classical diffusion equation is contained in the first line, and this is beyond the classical approximation. So the second one is going to be derivative suppressed. So there are Feynman diagrams, corrections, that loops that you can do. So I'll skip all of that. Basically, what I want to end here is, I want to end with the summary of these EFT methods. So when you think about the EFT, there are some technical details, but here is the big picture. Think about the big picture of the effective field theory of hydrodynamics is like this. There are two types of fields, the R-type field and the A-type field. So R-type field is a classical field, and the A-type field is the ones that tell you about stochastic and quantum fluctuations. The action is organized as a power expansion in A-type fields. Okay, so this is your expansion. The terms that are linear in A-type fields, F is whatever the equations of motion of classical fluid mechanics. So these terms contain all the non-linearities of classical hydrodynamics, all of your constitutive relations to all orders and the derivative expansion, they sit here in the first term. The term that is quadratic in the A fields, these describe the noise. Some of these quadratic terms are fixed by the fluctuation dissipation theorem in terms of the classical transport coefficients, such as the viscosity and conductivity. So in other words, if you start with the classical fluid mechanics, you can bootstrap yourself to the second line by using the fluctuation dissipation theorem. You can figure out what the second line is. However, there are also terms that are quadratic in the noise that are not KMS transformation of the classical equations of motion. So these terms will be invisible to classical hydrodynamics, but they will be visible in classical correlation functions through loops. And these terms, which are high order in A, they're completely invisible to classical hydrodynamics. Okay, so these are what we call stochastic transport coefficients. And the thing is, so these are things that you do not see in the classical equations of motion, but these are the things that you do see in the infrared correlation functions. So this is what I already said in words. They contribute to measurable correlation functions such as, particle density, or energy density. So these new stochastic coefficients will contribute to those correlation functions through loops. They will give rise to infrared effects that, okay, so they're derivative suppressed, but they're still there. These are different effects from the normal long time tails. If you want to think about the Kubo formulas, these stochastic transport coefficients, they can indeed be matched to the UV of the theory, like the normal Kubo formulas do. But what you will need non-retarded functions. Normal Kubo formulas require retarded functions, but these ones will require non-retarded. And so what this tells you is that somewhat a counterintuitive kind of claim that is counterintuitive from a point of view of classical field theory is that if you know the macroscopic classical effective theory to all orders in the derivative expansions, it is not enough for you to reproduce the macroscopic infrared correlations. So this is different from standard QFT. Of course, the difference is that the Schwinger-Keldysh EFT, and you need to enlarge your set of fields. So, all right. So I'll stop here. I say thank you for listening. And if you don't remember anything at all from this talk, just remember this one thing, is that there is more to classical hydrodynamics than what you see. There is more to classical correlation functions than what you see in the constitutive relations. Thanks.
Yeah, thank you very much for this very nice talk and very inspiring talk. Are there questions? So maybe let me ask a question first. So I'm now convinced that these new stochastic transport coefficients should exist, but do you think they're really completely independent, or there's a way to at least not fix them, but to constrain them and later on to fix them in a theory? Or
I think they're independent in the sense that they're coefficients in the action, right? When you write down new terms in the action, new terms, high derivative operators, they will come with their own coupling constants, right? So these are, coupling constants for certain types of operators that appear in the Schwinger-Keldysh theory. So these operators, they're not related to other things through the symmetries that, we think we sort of know. And so I would say that, yes, these are independent, just like, viscosity is independent from electrical conductivity. I would say that, these things are also independent, like independent data in the effective theory. Now, if this is something that has been on my list to work out, is that there has been more than one group working on the holographic formulation of this Schwinger-Keldysh effective action. Holography is not probably going to be useful for performing loop calculations, because once you have an effective action, you can just do a loop. You don't need holography for that. But holography can be useful in order to actually, just like holography can be useful for deriving what viscosity, conductivity, diffusion, normal transport coefficients are, it can potentially be useful for also deriving for those stuff, for what those stochastic transport coefficients are. Holographic Schwinger-Keldysh theories, I imagine there even have been talks on Holotube talking about that. However, from what I understand, most of what people have done was focused on the formalism, and I would say there's more things can be done with like relating those Schwinger-Keldysh theories to actual observable, correlation functions. Energy density. So that's something that's physical.
Okay, are there further questions?
Yeah, I have a question. Hi, Pavel.
Hi, Blaise.
So, listening to your talk, would you then say that besides holography, there's really no physical reason to care about higher derivative correction to hydro beyond first order?
Well, it's a big big statement.
If hydro is going to break down in any case because of fluctuations before second order corrections can kick in, then
so I knew about these fluctuations, of course, for many years, and this was one reason why I never cared about second order hydro when I was a student or a postdoc. But over time you become hopefully wiser, and you sort of soften up, and I think formulating hydro as an effective field theory really clarifies things. And for me, it really has clarified things. So the second order hydro coefficients, these are genuine coupling constants in the Schwinger-Keldysh effective field theory, right? So if you look at those correlation functions that I showed, so it so happens that the effects of those coupling constants that come multiply second order operators, for those correlation functions happens to be less important than the one loop contribution coming from first order theory. However, this is a formal statement, right? So in practice, the coefficient of the this first order terms can be small, as happens in holography with large n, or it just can be numerically small, right? Or if you are, if your measurements are precise enough, which is wishful thinking, but if your measurements happen to be precise enough to distinguish these contributions, the non-analytic contributions and analytic contributions, then you can extract those things. So this is one comment. Now another comment is that from in classical hydrodynamics, Israel Stewart and Avi Stokes or whatnot, and this classical hydrodynamics has been formulated so far in such a way that the causal hydrodynamics, such as Israel Stewart, is that the first order corrections is sort of trustworthy, and then the second order corrections are sort of contaminated by UV. I want to see a version where this can be done order by order. In other words, what is the causal hydro where the second order corrections are trustworthy and but third order is contaminated by UV, but everything is causal, admits well-defined initial value problem, equations are hyperbolic, or can you do it with first and second and third order are trustworthy and then higher order contaminated by the UV, which ensures the causality? Maybe it's impossible to do so. Maybe it is possible to do so.
Is it clear why it kicks in between first and second order? What controls this?
You mean
to some extent,
you mean the fluctuations, or
yeah.
in the classical theory?
The fluctuations. It's dimensionality, right? To some extent.
Well, yeah. In two special dimensions, they already kick in at first order.
Mm, yes.
And at one dimensions, they will kick in at perfect fluid order. So it's the normal thing. The less dimensions you have, the more important the infrared effects are. But I sort of presented these things in such a way that, okay, yes, omega to 3/2 is more important than omega squared, and it is true. However, if this is what we looked at, and so let me pull up this slide here. So this is what we looked at in our paper with Guy and Paul. So we took this expression here, and this comes with a well-defined prefactor. It depends on the equation of state, twos and pi's, whatnot, and we say, okay, so let's take QCD. So QCD is not large n. Well, this n is equal to 3, but is n is equal to 3 large for this particular purpose, or is it small for this particular purpose? And there are other things. The equation of state you can get from lattice QCD, and you can then in QCD, quantitatively, estimate the importance of this term. You know exactly what the prefactor is, and then because you know exactly what it is, you can say, well, what are the, like, is it more important or less important? Or is it like, how does it compare even to the first one? So formally, I would say formally, yes, it it is omega to 3/2, just like formally, in this example of perturbative quantum gravity, which you're familiar with, right? The one loop correction due to the graviton exchange is a power law, which is more important than the classical stuff that comes from high derivative gravity. So does it mean, high derivative gravity, you should not do classical high derivative gravity? Well, no. But, if you're just interested, in this particular question, and if you want to, compute the gravitational potential, very, very precisely, then, yeah, then you have to worry about those effects.
I have a question also actually about the related issue. Hi, Pavel. So about the power omega to the 3/2 thing and the coefficients in front of it that you say is roughly of consists of 2 and pi. I mean, is it universal because you're looking at linearized perturbation around stationary fluid?
Well, it's
so what universal in this sense, like omega to 3/2 maybe, but the coefficient.
Well, it's universal in the sense it does not depend on the cutoff. Unlike this one. So there's 2's and pi's in the equation of state. So, and it does not come from linearized perturbations. It does come from here, right? And this coefficient is, of course, universal by boost invariance. So once you have boost invariance, then you have this term with the coupling constant, which is what it is. It's E plus P by boost invariance and not something else. So it's in this sense, it's universal. But most importantly, it's universal in the sense it does not depend on the cutoff. It's only determined by the equation of state.
Okay, thank you.
Okay, we have got a few more questions. So the first one by Lorenzo Gavassino.
Hello. Thank you for your talk. It was very interesting. So I play more with the toy models and the PDA, so I'm not really an expert on how Kubo formulas are calculated. And so I would like to ask you this question precisely about these omega to the power 3/2 corrections. I see that there are some papers around in which they say they compute also that the famous tau, the relaxation time for Israel Stewart from the Kubo formulas. My question is, why don't they get an inconsistency? I don't know, why don't these effects somehow spoil directly the calculation? Why isn't it observable in those works that I have seen?
Well, it is supposed to be. So strictly speaking, right? So if like what is the Kubo formula, right? If you wish to use this expression that is, that is in the first line here, if you want to use this expression and define the Kubo formula for tau pi as, the second derivative of this expression with respect to omega, then yeah, this term will give you trouble. Then strictly speaking, from that point of view, the Kubo formula for tau pi does not exist. And I must emphasize so what I'm talking here is not something like new or controversial. So really the physics of that is coming from like 1970s.
No, yes, absolutely. I have also read the original Newtonian paper. I see that these green function, that the corresponding coefficients diverge. But I was just wondering why there are several papers in which they really give you some, they also calculate the tau from a Kubo formula and they don't problems. Maybe.
Well,
maybe
it depends on the approximation that you work with, right? So if you work in a weakly coupled theory, then in a weakly coupled theory, this coefficient here will have a higher power of the coupling constant than, for example, than the coefficient of tau pi, right? Also, if you work in a large n theory, then this will be like 1/n suppressed, but the second order will not be 1/n suppressed, right? So if you work in those approximations, then you can, yes.
Okay, so there is always something like this that comes into play and makes this effect disappear. Okay, thank you. Thank you.
So Sasha, please.
Hey, Pavel. Hey,
hi, Sasha.
Nice to see you. So I have sort of a bit confusion. I don't really know how to really formulate my question, but okay, so I'm curious about these new terms that you're saying, right, will contribute to the correlation functions, which cannot be parameterized by the hydro coefficients. Yeah. So should I understand, maybe sort of the way I think I understand this is that somehow when you compute, let's say, a fully retarded correlation function and you have to sum over loops, then it's clear that you have to sum over, you know, RA, AA, and all of the other correlation functions. And this is what you now have new terms for in the effective action. So
yes.
Therefore, you're summing over all of them, right?
Yep.
So that's sort of what I kind
yes,
of,
yes.
That I understand and I believe.
Yes.
Now, my question is the following. So normally, of course, you can, and it sort of goes to maybe even an axiom of quantum field theory. I mean, these correlation functions do follow from some analytic continuation of the other ones. Now, of course, are you saying that now, because this is an effective field theory, you cannot analytically continue from RA to AR to AA to RR? Or are you saying, so like, why is this not a problem when you compute Feynman correlators in you know, let's say chiral perturbation theory? Why do I not worry there that I need RA, AR, all of them, for example? You know, I mean,
well, I don't think it's necessarily a problem, and I don't think it's a problem here either. So once you know, we think about you know, Schwinger-Keldysh theory as just, you know, here is our field theory, here is our set of fields. And, you know, with this set of fields, we have the symmetries. We write down, you know, all operators consistent with the symmetries made out of our fields with some coupling constants. And then it's just like the normal QFT. So the difference is that we are somehow so used to like the classical interpretation of hydrodynamics. And the classical interpretation of hydrodynamics is something that, of course, only sees 1/2 of those degrees of freedom, only the R-type fields. Right. And so because we are so used to thinking about, you know, classical physics as made out of classical, you know, macroscopic variables, so that's maybe slightly counterintuitive. But if you think about classical physics, okay, this will be like bad terminology, but if class is by classical, you mean just something that sits in the action. If you just take the action and don't do path integral, you know, if by that action you mean classical, then of course it's just counting how many fields you have and how many operators you have of different of a given structure.
Do you think it's possible that these terms could be somehow constrained from the other ones that are hydro, let's say, from something like unitarity, or if I go to or reflection positivity in Euclidean theory or something like this, you know, sort of, I'm just trying to understand like why. So let's say you forget about, you know, so the only reason why we care about Schwinger-Keldysh is because we're doing real-time response and you need retarded correlators, right? Otherwise, we wouldn't worry about Schwinger-Keldysh. Now, let's say you're computing, I don't know, scattering amplitudes in QFT, and you're doing chiral perturbation theory, and you have your, I don't know, first term, second term, third term, and you can compute them from QFT, and there's some numbers there, right? Some coupling constants. What would, you know, would something similar also happen there? Are we forgetting half of the Lagrangian to compute pion scattering amplitudes? Or are we missing half the data? Or I mean, a little, you know, so like I completely understand what you're saying, and I believe it because I can see it.
Well, you yourself worked on this, right?
Right. Yeah. So, but I just don't quite. Yeah, I'm just trying to sort of think why this. That's why I can't even quite fully formulate the question. But would this also be a problem if you were computing Feynman correlators? You know,
I don't think so. It depends on what is sort of what is the like what is like what is the ground state, and what are the fluctuations on top of the ground state. Mm-hmm. If you do normal near vacuum EFT, then the vacuum state is, you know, is vacuum, and you know, you have infinitesimal perturbations of the vacuum, particles who we scatter. So it doesn't sort of make sense to talk about R and A fields there because a single particle is not a classical object, right? So the usefulness of the R-type fields is because we are sort of doing an expansion about a background that is, a classical background. So what these things will do, these things will do, like if we think about like not hydro, but like other types of EFTs. So if you look at and expanding about a classical background where the field itself has, macroscopic occupation numbers, then with those questions, I think you will also need these other coefficients. I think the reason we don't normally care about them in near vacuum physics is because we're expanding about the background that doesn't have any R fields.
No, it's true. I mean, certainly all of textbook QFT is, in vacuum to out vacuum at asymptotic infinity, and you just kill everything. I mean, yeah, but that's true. So, okay. No, I don't want to keep you for too long. I was just trying to understand if there was maybe a way to understand these other terms by some analytic continuation, because RA terms are supposed to be related to AR.
This is an excellent question, and I wish I had something intelligent to say about that.
I wish I was able to formulate the question better, but okay, maybe at some point I'll, yeah, okay, anyway. Okay, that's okay, thanks.
Okay, let's first of all stop recording here. I guess we are out of the question session.